Hello and welcome to yet another lecture on chemical engineering thermodynamics. Today we are going to study entropy and open systems, a problem on compressors. Let's take a problem. A compressor is used to compress gas. It enters at 1 bar, 290 Kelvin and is discharged at 10 bar. Find the discharge temperature. On the right hand side, I have made a figure of the compressor. It's a schematic of the compressor. The flow rate of air in this compressor is 2.5 moles per second. The air enters at 1 bar 290 Kelvin and leaves at 10 bar. The temperature at the outlet is not known. First, we apply the mass balance equation to this compressor. dN by dt, that is moles of air in the compressor, that is within the volume of the compressor. We take the walls of the compressor as the system. So moles of air changing within this control volume by time is nothing but the summation of the air flowing in and out. Now, since it's a steady flow problem, it's a steady state, we are going to have dN by dt is equal to 0 because no air is accumulating in the compressor. Whatever air comes in, the air goes out. Therefore, we have that the flow in is equal to flow out, which is 2.5 moles per second. The surrounding temperature is taken as 273 Kelvin. Now, the inlet enthalpy with reference to the surrounding temperature is 29.3, which is nothing but the Cp of air into 290 minus 273, that is 498.1 kilojoule per kmol Kelvin. The outlet enthalpy H2 is 29.3 into T minus 273. As we have noted that T is unknown, we take the steady flow entropy equation. ds by dt is equal to summation of n dot s bar summation of q dot by t plus s dot gen. For this, we take the compression as being reversible. There is no heat lost during compression and it is operating at steady state. Therefore, the LHS ds by dt is cancelled off and it is 0 because it's a steady state process. Now, summation of Q by T is cancelled off and it is 0 because no heat is lost from the compressor. Since the process is reversible, we take entropy generated, that is S dot gen, for the compression as 0. So we get S1 bar is equal to S2 bar. The entropy at the inlet of the compressor is 29.3 into ln 290 by 273 minus 8.134 ln 1 by 1 because we are calculating the pressure or the entropy at 1 bar pressure and the inlet temperature. So we get the entropy as 1.7699 kilojoule per kmol Kelvin. Since the entropy in is equal to entropy out, it was a reversible process. It is a reversible process. We get the temperature as 557.38. We just write the formula for S2, which would be 29.3 into ln of T divided by 273 minus 8.314 ln 10 by 1 and equate it to the value of S1, that is 1.7699. From that, we will get the temperature as 557.38 Kelvin. Therefore, the outlet enthalpy is going to be 8332.334 kilojoule per kmol Kelvin. Now we use the steady flow energy equation. du by dt is equal to summation of n dot h bar, that is the specific enthalpy, q dot, that is the heat added to the system, ws dot, that is the shaft work done on the system, and minus pdv by dt, that is the external pressure work or the volume work done on the system. Since we have taken the system as the compressor, the solid body of the compressor, the change in volume of the system divided by time is zero. That is minus P dV by dt is zero. The compressor does not lose heat, therefore Q dot is zero, and it's a steady state process, therefore du by dt is zero. And we get summation of n dot h bar plus ws is equal to zero. Putting the value of h1, h2, and n in this equation, we get the reversible work for the compressor as 19.59 kilowatts. Now, what happened if the outlet temperature of the compressor is 577 Kelvin? Find the delta S for the compression, the work required for compression. Now the entropy at the outlet stream of the compressor is S2 29.3 577 by 273 minus 8.314 ln 10 by 1. So we get 2.7835 kilojoule per kmol Kelvin. Since no heat is lost in compression and it is operating at steady state, therefore, again when we apply the steady flow entropy equation, ds by dt is 0, summation q by t is 0. But mind you, now we have a temperature 577 Kelvin, which is greater than the reversible temperature, discharge temperature that the compressor would have. Therefore, there is some irreversibility in the compression. And therefore, S dot gen, this cannot be cancelled out. And we get m dot S2 minus S1 is equal to S gen, or the change in entropy of the compression is equal to S gen, which is going to be equal to 0.0002534. What we do is we put the value of S1 here, we put the value of S2 here, and we put the value of n dot here. N dot is 2.5 moles per second. S2 already we have calculated, it is 2.7835, and S1 has been already calculated, which is 1.7699. So we put all these values and we get the entropy generated as 0.002534. Since the compression was irreversible, we have got a positive value of Sgen. The value of Sgen for a reversible process is 0, and for an irreversible process is positive. Now the discharge enthalpy of the compressor is 8907.2. Therefore, by applying the steady flow energy equation, which is this, once again with usual cancellations, you get the shaft work as 21.022 kilowatts. As you can see, the work required has increased. Now it has increased due to irreversibility in the process. So whenever there is irreversibility in compression, the discharge temperature of the compressor goes up. Now these irreversibilities come due to friction in the compression, and therefore the discharge temperature goes up. Hope you have understood. If you have any queries, any doubts, do put it in the comments. Well, this was all about the compressor problem and using entropy, the ideas of entropy to solve it. Have a great day.